Hello everyone, welcome to lecture 58 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on microwave metamaterials patterning methods. So here is the lecture outline. We will have a brief overview of optical lithography or photolithography and different non-optical lithography techniques, and then we will discuss in details the lithography methods for microwave metamaterials. We will first start with photolithography techniques, then inkjet printing, and we will do a comparison of traditional lithography versus the inkjet printing. We will then discuss the PCB based lithography and then 3D printing techniques. So, lithography is the process of applying a pattern onto a substrate surface, which is later transferred to the substrate itself. So, when we talk about optical lithography, it basically uses light to replicate a pattern from a photomask onto the substrate, similar to the traditional photographic reproduction. Okay. So, it basically involves a photosensitive polymer, which is also called photoresist, that is applied to the substrate, and when it is exposed to light through the photomask, it basically results into a patterned photoresist. So, various photolithography techniques exist, includes contact, projection, immersion and interference methods, which basically uses different types of light such as UV, deep UV, extreme UV and X-rays. So, different lights are used for different types of resolution, okay, of the structure that you want to pattern. So, we will see that later. When we talk about non-optical lithography methods, they basically use electron beams. So, it is called electron beam lithography or EBL, or ion beams, something like focused ion beam lithography, so FIB, okay. And then mechanical forces, something like nano imprint lithography. These are different non-optical lithography methods to create patterns on the resist film. So, each lithography technique has its own advantages and disadvantages or limitations in terms of the resolution, throughput and suitability for different applications, and that is why all these different methods are important, because they are used in different scenarios. In photolithography, that means you are using light sources, UV light sources. You will see that these are the widely used ones in photolithography, because of their ability to provide better image resolution and also the availability of UV sensitive photochemicals. So, mercury vapor lamps are typically the dominant UV light sources used in photolithography, which emit lines at 405 nanometer or H line, 365 nanometer I line and 254 nanometer. Okay. Among these, the 365 nanometer, that is the I line, is the most commonly used one. Now, there are deep UV light sources such as excimer lasers that operate at 248 and 193 nanometer. So, these have been adopted to achieve higher resolution in lithography, right. Now, an excimer laser is basically, it's a short for excited dimer laser. So, it is basically a type of laser that could generate intense UV light via the use of excited dimers or molecules. So, unlike most lasers that rely on stimulated emission from atoms or ions, these excimer lasers basically use a combination of noble gases and reactive gases to create a laser medium. Then you have extreme UV sources that are under development at 13.5 nanometer that can help you in advanced lithography applications. So, in lithography, it is critical or crucial to ensure uniform illumination intensity across the entire substrate surface, which basically requires shaping the beam into a flat speckle free profile to avoid any undesirable effects. Now, when I say speckle free profile, that basically refers to the desired outcome of the lithographic process, where the pattern of the image that is produced on the photosensitive material which is also called photoresist, okay, that should be free from speckles or unwanted noise. These are basically the noise that comes from the interference patterns. Okay. So, the speckles in the lithographic pattern basically can degrade the quality and precision of the final image, especially where you require very high resolution and fidelity, something like in semiconductor manufacturing. Now, other than the light source, the second important parameter in the photolithography is basically the photoresist. Okay. So, photoresist composition and their behavior decides how you are going to do the lithography process. So, photoresist are nothing but photosensitive materials. They are basically composed of photoactive compounds, a resin and a solvent. High molecular weight polymers could dissolve in organic solvents, and they are temporarily coated on wafer substrate. So, this is where you have your silicon substrate and then you have a thin film. On top of that you do the photoresist coating. Okay. And then whatever the design that you want to transfer, that you do via, you put a chrome mask like this and then you do the UV exposure. So, through the gaps UV light can go and hit your photoresist, and this is how you are transferring the design from the mask onto the photoresist, right. Now, how do you apply the photoresist? You basically use spin coating method. So, this is nothing but a rotating platform, okay, on which you have the substrate. On top of that you put this precursor solution and then you spin coat it. So, from the centrifugal force you will get a very uniform spread, and after that you expose to UV light, and this photoactive compound will release chemicals that increase the solubility of the resin. Okay. So, this can makes it either you can go for positive or negative tone photoresist. So, once you put this exposure to the UV light, okay, what is happening to the photoresist? They basically undergo chemical modification, and then a developer solution is basically used to etch away the modified or the unmodified parts of the photoresist. So, this is where the exposed regions. Okay. Now, there are two ways of doing it. So, either you can etch away the exposed parts, okay, then you get the positive tone photoresist, and if this parts only retain and the remaining photoresist can be removed, that is called the negative tone photoresist. So, that is how the pattern that you are transferring that can be achieved. So, typically the exposure in photolithography is measured in millijoule per centimeter square, and the exposure is basically calculated by multiplying illumination intensity, okay, that is milliwatt per centimeter square, by the exposure time. So, you get the millijoule per centimeter square, and the typical dose in photolithography would range from 50 to 500 millijoule per centimeter square. Okay. So, as we discussed, there are two variants of photoresist. The one is the positive photoresist. So, there what happens, the exposed region becomes more soluble and that can be easily removed in the developing process. Okay. In the case of negative photoresist, is other way. So, your polymers basically get combined to a photosensitive compound, okay, and this compound basically absorbs the radiation energy and converts it into some sort of chemical energy into a chain reaction, causing the cross linking of the polymer molecules. In short, they become this linked polymers will have a very high molecular weight and they become insoluble to the developer solution. So, this part will not dissolve, the remaining will get dissolved. Okay. And after the development, the unexposed portions are basically these two, that will be removed. Now, if you consider a professional producing materials in the microelectronics industry, they would have definitely heard of this negative photoresist. It is an essential tool that is used to create accurate and precise electronic components on various substrate, and a negative photoresist basically serve as integral layers for successful device fabrication, enabling microfabrication engineers to develop structures that would otherwise not be achievable with the conventional etching methods. So, understanding how to utilize negative photoresist effectively can make all the difference. So, as you understood that negative photoresist is basically a type of photosensitive material that is used in this photolithography process that can essentially create the pattern on the substrate. So, here you after exposure the solubility of this material increases, so the developer solution cannot etch it out, right. So, that is the only difference as compared to the positive photoresist. Next important component is the photomask. Okay. So, photomasks are nothing but glass substrates that contains opaque metal patterns typically made of chromium that could block the UV light transmission. Okay. So, this is a schematic representation of a photomask, and then you have a lens, and this is how on the photoresist these patterns are being transferred. Now, the creation of the photomask basically involves standard photolithography process, where you again need to apply photoresist, exposure, and then you transfer the pattern to the underlying chromium layer. And then you use UV light sources such as helium, cadmium or argon fluoride lasers to typically scan a laser spot across the surface, which is controlled by a software containing the photomask design. And then electron beam lithography can be chosen if there are small features. Okay. So, once that is done, you can think of the mask alignment and the exposure. So, for alignment and exposure tools, there are basically three different types of photolithography, you can say. One is the contact printing, then you have proximity printing lithography, and then you have projection printing lithography. So, the first one we will discuss is the contact printing photography. So, here you can see it is a very simple equipment, okay, that was typically used before mid 70s. Okay. What is happening here is that the mask is basically in the contact. Okay. So, there is a direct mask and wafer contact, and that limits the mask lifeline or lifetime. Okay. And the resolution is typically submicron. Okay. So, there is a UV lamp, there is a lens, and then you can allow the light to come through this mask as a parallel wave, but then because they are having a contact here, the lifetime of the mask is reduced. Then you can also see that in this contact photolithography, the photomask basically comes in direct physical contact with the photoresist coated substrate, but in reality you will see that achieving a perfect zero gap across the whole mask is practically impossible. So, typically what gets in between is the microscopic dust particles, or there could be surface roughness, or the mask may be bowing often due to some irregularity in the surface, and that will introduce some tiny unintentional air gaps, which is typically some tens or hundreds of nanometer. Though these gaps are not intentional, but they will still cause some diffraction effects and pattern broadening. That means the degree of contact critically impacts the resolution of the patterned substrate. Okay. So, this kind of work is still used in research labs. So, here you can see the aerial image that can be approximated mathematically. Okay. So, the minimum Gaussian aerial image width can be related to the photoresist thickness Z, the air gap thickness S, and the UV wavelength lambda that is being exposed. So, you can find out the minimum Gaussian aerial image width to be equal to 3 by 2 square root of lambda S plus Z by 2. Okay. Now, it is essential for thick photoresist and double sided alignment exposure. Okay. So, this particular contact lithography. Okay. And what are the applications that include advanced 3D packaging, optical devices, and MEMS. Now, there are some challenges, as I mentioned, that because of these small unintended air gaps, they will have some diffraction effect. So, some cases you can see that the patterns are getting enlarged, or there are loss of accuracy, and most importantly, because there is direct contact, the mask will get damaged and contaminated. So, the next method, okay, which is better than this one, will be the proximity printing photolithography. As the name itself tells you that in this method you introduce a controlled air gap, typically a few microns or you can say tens of microns, that is deliberately introduced between the mask and the substrate. So, PR is the photoresist layer, this is the substrate and this is the mask. Okay, you see these are the openings through which light can get in, and this is the pattern that will be transferred. So, what the good thing here is that there is no direct contact of the mask, and the mask distance is typically 10 micrometer from the substrate. So, here the air gap is intentional and it can avoid mask damage and contamination. So, it results in longer mask lifetime. The resolution is typically greater than 3 micron in this case. So, what is the drawback in this particular method is that the resolution decreases due to stronger diffraction because you are maintaining a larger gap. Okay. The third one is projection printing lithography. So, here you have this mask, this up till here it is the same. Okay. Then you have a projection lens. Okay. So, this is the new optical imaging system that you are using in this particular method to project the image of the photomask onto the substrate from a distance. Okay. So, this is just like an optical microscope, okay, and the resolution conditions are also very similar. So, here the resolution limit is given by r equals lambda by 2 Na. Na is basically the numerical aperture of the projected beam into the substrate. That basically tells you about the capability of the lens to collect the diffracted light. Okay. So, projection lithography is widely used in semiconductor manufacturing and microfabrication processes. So, the main two applications are semiconductor IC fabrication and micro electromechanical system, that is MEMS fabrication. Okay. Here you get very good resolution, right. So, the next method we will be discussing is inkjet printing. So, inkjet printing is an additive manufacturing technique that basically deposits conductive inks, often which contain silver nanoparticles or MXene, onto a substrate. So, it is basically low cost and direct additive manufacturing technique that can be used for creating metamaterials. It enables the rapid fabrication of structures like microwave absorbers and metal lenses on various flexible and transparent substrates such as paper and PET films. So, this particular process basically uses conductive ink, okay, to deposit precise pattern of metallic resonators on dielectric substrate. Okay. So, this allows for flexibility and creating specialized properties such as high absorption or transparency at specific frequencies. So, here you can see an electrically driven piezoelectric accelerator can basically generate a pressure pulse which will eject a fluid droplet from the nozzle, okay, and the coordination between the electronics and the motion system will enable digital patterning of complex layout on planar substrates. Now, we will see how inkjet printing works for metamaterials. So, the first thing would be the ink formation. So, you consider conductive inks which are commonly containing silver nanoparticles or materials like MXene, okay, that is typically used for inkjet printing. And then you do the substrate selection. So, you go for dielectric substrates such as paper or flexible polyethylene terephthalate, or you can say PET in short, PET films, that can be used as the base for the metamaterials. And the third step would be the pattern deposition. So, here the inkjet printer basically deposits the droplets of the conductive ink on your substrate, forming a precise metallic pattern, just like here you can see, or you can do any split ring resonators or any other structures that constitutes unit cells of the metamaterial. And next, you can also think of layering, that means multiple layered can be printed, including ground planes or other conductive elements that can create complete metamaterial structure. Next, after printing is done, you have to post process it, that is you have to do annealing to enhance the conductivity of the metallic features. So, that is how you do the printing of the metamaterials. So, where are the applications? First thing, you can make metamaterial absorbers using this inkjet printing. So, inkjet printing can create metamaterial absorbers for different interesting applications like stealth technology or electromagnetic shielding, that is electromagnetic interference shielding, EMI shielding. You can also use them for antennas and metalenses. So, you can fabricate metalenses for focusing or shaping electromagnetic waves and metamaterial based antennas to enhance performance, as we already discussed in this course earlier. You can also think of flexible metamaterial structure. So, it basically enables the creation of flexible circuits and flexible metamaterial absorbers for microwave frequency range. So, here is a comparison of the traditional lithography versus the inkjet printing method. You start with copper clad substrate in both cases. Then in the traditional lithography method, you first coat etch resist on the substrate, then you align the photomask and do the exposure, UV exposure, and then you develop the etch resist. Okay. On top of that, you have to remove the copper metal, and then you also remove this etch resist, and you get your pattern here. In the case of inkjet lithography, what do? You etch resist ink jetted on the substrate. Okay. So, you put it like this. On top of that, after that is done, okay, you can basically etch the copper metal, okay, and then you strip this etch resist ink, okay, and you got the pattern done. So, this is how typically it will look like after jetting ink and after etching and the ink strip. So, this is how you get your final PCB or the metamaterial fabricated. Okay. Now, we will look into PCB based lithography. So, PCB is printed circuit board. PCB lithography is a subtractive manufacturing method that basically uses a series of steps to create metamaterial structures on a PCB board. So, it is a technique for creating 2D or planar metamaterials by etching or printing desired patterns onto a substrate, typically on a FR4 board. So, it works by transferring a desired pattern onto a resist coated substrate. So, this is how the raw material of the PCB will look like. So, you start with the dielectric board, then you take copper foil on both sides or one side, and then you send it through the laminator. So, you get the copper laminator on a dielectric board, okay, and then you have the resist being coated here, and then you put the circuit image. On top of that, you etch the resist and you print the image, okay. And finally, you do the circuit etching, that means you etch the material out. So, what you are left with only the pattern on the dielectric. Okay. So, this is basically the copper pattern on the dielectric, right. So, this is how the unwanted material will be etched away and you will get the precise pattern on the metamaterial. So, why it is important? Because it enables precise creation of microwave and electromagnetic structures on PCBs, and it is a key manufacturing technique for microwave metamaterials because it is scalable, cost effective, and it produces large scale planar substrates that are needed for microwave frequencies. Now, what are the key steps in PCB fabrication? The process basically transforms a digital design into a physical board through a series of additive and subtractive steps. So, you start with the dielectric board and a copper foil, and then you finally get a dielectric board on which a copper pattern is basically printed, right. So, what is the first step here? You have to go and design the PCB layout. For that, you can create the circuit or the design of the metamaterial using any electronic design automation software, EDA software. Okay. So, there you create the schematic and convert it into a PCB layout with the component footprint and routing. So, once it is done, you print the layout. Okay. So, that means you print the design. So, that means you are basically printing the final PCB layout onto a transfer paper or a transparency sheet using a laser printer or inkjet printer. So, this print is the mirror image if you are using the toner transfer method. Okay, and then you prepare the copper board. Okay, so you need to cut the board. So there is you take this copper clad blank board and you cut it to your desired size of the PCB, and then you got to clean the surface of the copper clad board to make sure that there is no dirt or oxidation, okay, standing on it. Okay, so you can also do a fine grit sandpaper. Okay, you can do a little bit of sanding to achieve a shiny surface. So you can also go for lamination and do multiple layer boards that are required for complex metamaterials, where you have multiple pattern layers stacked and bonded together under heat and pressure to create a single multi-layer board. Okay, so you can do the lamination also. Okay, finally you transfer the layout, so you can also use toner transfer. In this method, you basically place the printed design face down onto a clean copper surface, and then you use a hot iron, no steam, to basically iron the paper onto the board, and that will transfer the toner to the copper, right? Other methods include inkjet method that we have just seen, that you can directly print the layout using a conductive ink, okay, using the inkjet printer. And once the design has been done, the last step is this etching. So you have to apply the etch resist. For transferring, you have followed this method, and after it is done, you basically immerse your board in water to peel off the paper. That will reveal the toner or the ink pattern on the copper. So this pattern will basically act like an etch resist, protecting the copper traces that are going to form the circuit. Finally, you do the etching, that is here. So the unwanted copper pattern is basically then chemically etched away using a corrosive solution, leaving behind the desired conductive traces that will form the metamaterial pattern. The last important technique that we will be discussing today is the 3D printing techniques. So they are basically also the additive manufacturing techniques. So 3D printing basically offers a way to create complex 3-dimensional microwave metamaterials that are basically difficult to fabricate with the conventional planar methods such as PCB based method or inkjet printing or lithography. So in this 3D printing method, the technique basically uses metamaterial structures layer by layer building. Okay, so the common approach is that you print dielectric polymer structure with standard 3D printer, then you apply conductive coating via sputtering or electroless plating. You can also use some advanced option where conductive filaments can be used to directly print the metallic parts. Now, what are the advantages? Here you can have some design freedom in the Z direction. So it is well suited for rapid prototyping and low cost, and it enables creation of volumetric structures and gradient index, that is non-planar lenses. So they are also suitable for large structures like microwave antennas and radomes. So the applications of 3D printing techniques can be creating microwave lenses, complex antennas and broadband absorbers with unique 3-dimensional geometries. So there are few 3D printing techniques. The first one is called fused deposition modeling, that basically uses thermoplastic filaments such as PLA, polylactic acid, ABS, that is acrylonitrile butadiene styrene, and PETG, that is polyethylene terephthalate glycol modified. Okay, so these dielectric structures are basically printed in this method and then metallized via sputtering, silver paint or electroless plating that creates the conductive features. One example could be a 3D printed dielectric scaffold coated with copper for the split ring resonators. Okay. Then you can also think of stereolithography, SLA, or digital light processing DLP. They basically use photopolymer resin cured by UV lasers or projectors. So, they provide higher resolution 25 to 100 micrometer as compared to FDM, fused deposition modeling. Okay. And this SLA or DLP are useful for gradient dielectric metamaterials or sub-wavelength lattice structures. The third method is selective laser melting. So, this allows fabrication of all dielectric metamaterials or direct metal resonators. So, high mechanical strength can be achieved. These are good for antennas and also for waveguide based metamaterials. So, we will look into one of these FDM first. So, how it works? So, this is the step by step process for FDM. So, you have the digital design. So, that is a 3D model that is created using a computer aided design or CAD software. Then you do the slicing. So, the digital model is basically sliced into thin horizontal layers using slicing software. So, this software basically generates a toolpath that guides the printer on how to create each layer. Okay. And then you have to do the printing. So, this is the FDM 3D printing. So, this 3D printer basically heats the thermoplastic filaments such as ABS, PLA or PETG to its melting point. So, it basically takes the support material spool, and this is the model material spool like this. Then this is a liquefier that moves in X and Y direction, and these are the extrusion nozzles, and this is how you print the parts. Okay, and this is the platform which can move up and down in the Z direction, right. So, this is the foundation sheet on which it is fabricated. So, what happens that when you put these filaments, the molten metals are basically extruded, as you can see here, through nozzles, okay, onto this build platform, or you can say on the previous layer following the toolpath that is generated by the slicing software. Then you will have layer by layer formation. The material basically quickly solidify as it cool down, okay, and it creates a solid layer. The print bed or the nozzle basically moves in accordance with the slicing instruction to deposit subsequent layers until the entire object is formed. And after the printing is complete, the support structure, if they are used, will be removed, and the object might undergo some additional post processing like sanding, painting or other finishing techniques to give you the final product. Okay. So, what we saw that FDM is an additive manufacturing technology that basically uses 3D printing. So, it works by melting and extruding the thermoplastic filaments layer by layer, and it creates a 3-dimensional object. So, the advantages, as you can think of, that it's using 3D printing method. So, it is more accessible, cost effective and versatile. However, there are some limitation. The first one is the layer resolution. FDM prints can sometimes have visible layer lines and affecting the surface finish, and also there may be some support structures, something like objects with overhangs or complex shape that may be required to support the structure, which need to be removed after printing. So, you need to do some additional finishing work to come up with the final product. So, with that we conclude our lecture. If you have got any query, drop an email to this email address dept.sikdar@iitg.ac.in. Thank you.